The topic of my research is estimating extreme snow avalanche runout for the Columbia Mountains and the Fernie Area of British Columbia. And just to give a little outline of where we're going, I'm going to start with the really quick background on snow avalanche hazard mapping, why we do it and why it's important. From there, we're going to talk a bit about statistical runout models, and then the study areas and field methods where I was actually out collecting data, a little bit on the statistical model results, and then we'll touch upon the snowfall analysis as well. So I think I got the lighting right for the pictures here, but we might flip back and forth as we get to a few of them just to get better resolution. But what we're going to start with is to show a piece of avalanche terrain, and this is Highway 16 here in between Prince Rupert and Terrace in northern BC. And in this portion, the highway runs right along the Skeena River, and right through here, it's coming down from Assimilation Lake up above are several avalanche paths that you can see has trim lines in the forest here that descend towards the highway. There's about 6 paths here. And one of the key things, before we go into the frequencies, we'll just talk a tiny little bit about avalanche terminology. So when we're looking at an avalanche path and when we're talking about the bigger avalanches that occur in this path, we're talking about the ones that come right to the end of the runout zone. And quick terminology, we have 3 main portions of the path that we talk about. We talk about the start zone up here. So this is total elevation drop of about 1,000 meters. So up in the start zone, we're talking about the portion where the snow slab releases from the ground and picks up speed and starts to move. Slope angles above 30 degrees there generally. In the track, we're talking about the portion where a lot of snow is entrained and deposited. The slope angles are generally about 15 to 25 degrees, and this is typically where the avalanche reaches maximum velocities. And then out in the runout zone is where our slope angles are less than 15 degrees, and this is where the snow avalanche will sort of start to rapidly decelerate as it comes out to the flatter terrain. And we're just going to zoom in on the runout zone, and in any given avalanche path, we like to talk about the frequency that we have to points in the runout zone. So I've given some hypothetical numbers and distances here. So on a yearly basis in a path like this, we might have avalanches which reach the top of the runout zone. Maybe 5 years or 10 years, we might have avalanches that kind of come out to mid to lower zone. But the real question that we want to answer, especially if we're going to be investing money in building infrastructure like a road or a railway near the bottom of the runout zone, is where the 30-year or 100-year avalanche is going. So this is the question that we're trying to answer when we go to these sites. And last winter, 2010-2011, was a really exciting winter for people working in this type of avalanche work, because we had lots of extreme avalanches happen. So I just have a few photo examples here. This one is from the Selkirk Mountains, the Carnes Creek area. And in this case, we're actually looking at the other side of the valley. So the avalanche has descended here and come up the other side of the valley, and it's just sort of starting to round the bank here and head down the creek. And we see 50 to 70-year-old timber, which has been completely taken out by this avalanche here. Another good example, if anyone was trying to travel in between Revelstoke and Golden, there was lots of highway closures this winter. And this is one that happened at the Lanark slide path here. So avalanche coming down here and depositing all this timber on the road here, and that timber gain is in the 50-year-old type range there. And that's the Trans-Canada Highway running right along the bottom. And this is one of my favorite examples. This is actually from 2008 winter. This is North Juneau, Alaska, the Snettisham area, where they have a hydroelectric line that runs from out of town towards the town of Juneau. And this power line tower had been here for about 30 years, since the 70s. And in 2008, a springtime wet avalanche came down here, completely took out this tower and damaged another one. And the number that I like to put to this is that this resulted in the entire town of Juneau going from hydroelectric power to diesel backup. And the cost to consumers for electricity went from 11 cents a kilowatt hour to 54 cents a kilowatt hour for 2 months while they fixed that. So in Canada, we have some hazard zoning guidelines. We talk about the red zone, the blue zone, and the white zone when we're zoning avalanche terrain. So in general, the red zone, we're talking about high impact pressures and more frequent return intervals, and that's the area that we want to stay out of for any sort of permanently occupied structure. Blue zone, lower impact pressures and bigger return intervals. We may want to put something temporary in there or infrastructure through there. And in this example, the white zone is the area outside of here. So just to show what a zoning map looks like. And when we're really lucky in ideal circumstances, we can go into a piece of avalanche terrain, and we've had a recent climax avalanche, like this photo right here. This is from a mine site in northern BC, where the avalanche has descended here to the creek and up the other side, taking out hectares of mature timber. This is like 70-year-old timber here. So in this case, we've got a really good vegetative record of knowing where those climax avalanches can go. But in other cases, like this one here, this is from Blue River, BC, the vegetative record in the runout zone might be completely gone. So in this case, these avalanches are originating in the upper cut block, coming down here through the timber, and then are running out into this lower cut block. So we have no vegetative record there. So in this case, we need some other way to help predict how far these extreme avalanches can go. Some other examples of where we might have this situation is avalanches that run out onto lake ice, avalanches that run out into farmer's field, or up in the Arctic or high alpine, where we just don't get the vegetation growing. So in this case, we do have dynamic computer models that can help us estimate where we release snow at the top of the path and watch it move down the path. And these are all based on putting in a friction or turbulence coefficient. And when we put in this coefficient, it not only accounts for ground roughness and friction, but a lot of other changes in flow characteristics that are happening. And we need a lot of judgment with using these models in specific areas to rely on those results. So what I'm going to talk about is the second type of model, which are statistical runout models. So what we have here is a cross-section through a hypothetical avalanche path. We've got the top of the start zone through the track and out to the runout zone here. And the two important things on here are what we call the beta point, which is where our slope first descends to 10 degrees, and our alpha point, which is right here, or the extreme runout point, so the furthest point where we expect that avalanche to go. And there's two types of statistical models that I'm going to talk about today. The first one is alpha beta, which calculates our alpha point just based on our beta. And the second is our runout ratio, which also uses this beta point, but based on extreme value statistics. So the first work on this was done by the Norwegians for alpha beta and by researchers at UBC for the runout ratio. And here's a nice Google Earth picture of BC. And what we have here is showing the two regions where we have statistical model parameters that work. So these models have been developed for the Coast Mountains and also for the Rocky and Purcell Mountains. And in addition to this, we have a Canada-wide short slope model, so to deal with slopes less than 350 meters vertical, which tend to run a bit further. And what you can see is missing on here is the area where we do a lot of our research, the Columbia Mountains. And other than being known for the fantastic skiing that's there, there's also mining development and hydroelectric development. So a lot of other things happening in the mountains that make it important to know, be able to avalanche zone. And so the Columbia Mountains is my first study area, and the other one is the area around Fernie, BC. And for those of you who have been to Fernie, you know it's famous for its great skiing. And hazard mappers working in that area identified that when they were using the Rocky Mountains model, it wasn't accurately predicting in Fernie because the avalanches there tend to go so much further. So in the Columbia Mountains, we collected data from a number of sources, me out with other students doing fieldwork, also from the Canadian Avalanche Association provided some data, and some other consultants working in the area as well. So we ended up with 33 paths from the subranges of the Caribous, Monachees, and Selkirks. So these are all paths over 350 meters vertical, coming from a variety of start zone elevations and aspects. And in the Fernie area, our study area is much smaller. I've shown here Fernie and Sparwood. These paths we're going to revisit later, but for the Fernie models, we just use right in the Fernie area to develop these models. So when you talk to people in that area, they say the heavy snowfall in Fernie ends somewhere around here, but nobody can really draw a line on a map exactly where that is. And so what the fieldwork for this looked like was a lot of bashing through alder, so going right into the avalanche paths and collecting slope angles and also observations of vegetation from about the track elevation right out to the runout zone. So here's a photo of what a typical one looks like. Some of the vegetative evidence we were collecting was counting tree rings to actually age and date trees to get an idea of frequency in the runout zone. And this is a nice photo here. This also shows a tree that's been impacted many times by snow avalanches, all the branches on the uphill side missing. So collecting all these kind of observations to measure the beta point and figure out where that alpha point was for these paths. And don't get too caught up in the numbers here. This is just to show an example of some of the parameters that were collected for each path. So we have all these parameters that depend on that topographical profile, like the beta point, the horizontal distance to beta, the vertical distance to beta, matching a parabola to the path. And then we also have parameters that are dependent on the start zone. So the aspect of the start zone, the elevation of the start zone, similar with the runout zone. The surface roughness, we're talking about the ground roughness in the start zone, and the wind index as well. And just to come back to show the topographical profile again, so here's our matched parabola, and we're getting a few of our parameters from there as well. So we're going to just go right to the simplified results here. So we did multiple regression and also our simplified regression, which is where our really useful results are going to come from. And this shows the results for the Fernie area of our alpha-beta model. So we end up with an R-squared of 0.64 with our 30 avalanche paths from that area after throwing out an outlier. And similarly for the Columbias, except the data here looks a lot nicer. We have a higher R-squared here. And what we found in this case is the constant actually becomes insignificant, similar to other work done in those regions, or in some of the other regions. So we end up with an alpha-beta model here as well. And if we take these same data points, but instead analyze them with our extreme value statistics, for the Fernie area, we end up with a model that looks pretty nice here. And in this case, we're looking for higher R-squareds above 0.95 because both our variables are dependent on our runout ratio here. So this is just ranking our runout ratios, plotting the ranks and regressing there. And similarly for the Columbias, a slightly better match here as well. So these are kind of the key results of this study, and everything I've presented up until now has been based on methods that have been established by other people. So just applying existing methods to a new area. And what I'm going to quickly touch upon now is the second part, which sort of hasn't been done before, which is the snowfall analysis. So if we intuitively think about avalanche runout, we think more snow is going to equal longer running avalanches. All the work done on statistical models until now has defined these based on a regional basis, saying that geomorphology is part of it and climate sort of rolled into that regional definition as well, and that in any of these regions on a 100-year timescale, we'd see the optimal conditions to create these exceptionally large avalanches. So on the coast and in the Rockies, it would be the same. But what I tried to do is take the snowfall data that's out there and see if bringing in the snowfall data could help our prediction or help the analysis. So this slide's just to show what the data was we were working with. So here's 3 avalanche paths near Valemount. This location here shows a snow course station that's collected by the BC Meteorological Survey. And this is, the purpose of this data is to predict snowmelt in drainage basins. And the second source we have is Environment Canada maintains weather stations in valley bottoms, so in most of the communities and airports. So using these 2 data records along with a third one, which I'm going to show right here. So this shows a schematic of what's called the PRISM data set. It's developed by the folks at Oregon State University. They've done this for all across the states and for select regions in Canada as well. And what it is a 2-kilometer pixel showing average precipitation that we've converted into winter precipitation. So the darker blue areas here showing more and the lighter areas showing less precipitation. So we also extracted the value for each avalanche start zone to get a precipitation data point that way as well. Now, one of the difficult things when you're doing this kind of work is taking your valley bottom data and making it make sense up at your start zone elevation. So I used 2 published methods that are out there to make some interpolation between what was happening at valley bottom and what's happening at high elevation. The first one was 1984 work by Close and Shear. This was developed to help predict snow loads in buildings. So they have a quadratic relationship that they've defined on a mountain range basis to help predict mountaintop precipitation there. And also the Swiss, Margrethe and Gruber, for their modeling, they've used this 5-centimeter increase in snowfall for every 100 meters elevation as a general rule. So if we apply these corrections to our valley bottom data, we end up with this kind of noisy looking slide that shows sort of the lows that we're predicting along with the highs that we're predicting for each of these locations. So you can see a really, really big variation, like 400% in between the prediction methods. But I took this data anyways, and what we did was reduce the data set down to sites that had really close data, so say within 10 kilometers of the avalanche path, instead of some sites where we were working with 30 kilometers away. And once we reduced this data set, we could look at just the Pearson correlations in between our runout parameters and our snowfall, just to see what relationship existed there. And after looking a little bit closely at these relationships and throwing out some of the outliers, we found that the only ones that really seemed to hang together were relating the prism precipitation to the alpha angle, and also some of the snow course data corrected we could do as well. And doing a multiple regression with that, we found with the prism data, it gets tossed out on one of the first steps, so not really a very strong predictor there. And with the snow course data, that on a stepwise regression, it does stay in the equation. So there's obviously some relationship there. It's just trying to figure out how helpful this could be to people actually doing the work. And just to touch on some of the key uncertainties there, this picture shows a guy in Alaska standing above a steep avalanche path with a big wind-loaded cornice coming in the direction of the prevailing winds. And you can imagine trying to use a station 10 kilometers away to guess exactly what's happening in this area. And that's partly to do with how much wind transport's happening up at these elevations. And the second thing is that extreme avalanches may not be related to extreme snowpack. They might be more related to extreme storms. So it's having the data resolution to actually relate our 3-day precipitation or our 1-day precipitation to our long-running avalanches rather than our winter precipitation. So that brings me to the end of this presentation.